we will have second session of this module, which is about deep learning by Dr. Ayman. So we can start now, inshallah. Bismillah.
Bismillah ar-Rahman ar-Rahim. I'd like to welcome you to the second session about deep learning. So inshallah, in this session, I'm gonna have three parts. In the first part, I'll talk about neural networks, their structure, and I'm gonna show you like what we can have the neural networks learn. So from like design point of view, like for example, we can have them to implement logic functions, we can have them to detect boundaries, we can design them to do so. So this is the first part where I can show you what they are capable of. In the second part, we'll go over like how can we train such neural networks to learn by themselves, not us designing them, but what is the learning mechanism that we should do to make them learn basically whatever classification problem that we have. And in the third part, I'm going to talk about convolutional neural networks, which is a very important type of neural networks that has so many applications, especially in computer vision, image processing, and so on. So these are the three parts that I'm going to inshallah cover. And I'll have notebooks wherever we go over the material to demonstrate. So the outline of the first part is what are artificial neural networks. We'll talk about the neuron. We call it here the soft perceptron, which models like the functionality of the neuron, and then multi-layer perceptrons and how we can use them to model Boolean functions. And then we'll see how we can actually use them as universal classifiers. So neural computation, people have been thinking since like the early 60s how we could mimic the computations done by humans in the brain, and trying to study the brain and to see how computation is actually done in the brain and how can we build machines to mimic how the brain thinks. Lots of theories have been developed and thoughts and so on, but basically this led to the concept of neural computation, which stands for general machine learning approach that involves processing information in a kind of similar manner to how the brain works, which is composed of networks of neurons. In fact, billions of neurons connected to each other, trying to make decisions. So that's why the term is artificial neural networks, like to mimic the neural networks that are in the brain, are basically networks of neurons that are connected in a certain manner to try to approximate certain functions or what the brain is actually doing. So they are actually massively parallel, which makes them efficient, robust, fault and noise tolerant in their behavior. So if we look at the neuron, people studied the structure of the neuron. We find that it is composed of a soma, which is the cell body. And this has kind of dendrites that connect to other neurons. And then there's like an axon that transmits an information. So the soma makes a decision based on the information received from the dendrites, and it decides whether it fires a signal or not. And then that signal gets transmitted across the axon. And then there are like the axonal terminals that get connected to other neurons and so on. So this is like kind of the model or how the neuron is composed of. So people try to really mimic kind of the neuron by creating what's called the perceptron. So the perceptron is like the mathematical model of the functionality of the neuron. So you will hear me say neuron or perceptron, which mean basically the same thing, interchangeably. So in short, artificial neural networks are mathematical model that we use for learning that got inspired by biological neural networks. And they model the mathematical function from the inputs received to the outputs based on the structure and the parameters of the network. So what we need to do is we need to see what are the parameters that we need to learn in these neurons so that we can actually make them approximate a function or detect a decision boundary and so on. So the good news about neural networks is that we really don't have to tell them what they should learn and how they should learn. They automatically are going to decide how they should actually learn information and what type of information they should learn to reach to the solution or the decision boundary that we would like them to decidable, like classification problem, for example. So the mathematical model of the neuron, called perceptron or artificial neuron, looks like this. So for each input or feature that we have, we multiply it by a weight. And then all these basically inputs multiplied by weights get summed into a formula, which is just like the weighted sum of the inputs. And then this gets fed to an activation function that decides whether to fire or not to fire. Okay, so the activation function here, we will start with a very simple activation function. For example, if it is greater than or equal a threshold, it gives 1, otherwise 0. However, we can use actually nonlinear activation functions like the, for example, the sigmoid function, the tanh, and others that will add some nonlinearity, which makes the neural lens better. So we look at the neural nets in a structured manner. So the first layer, we call it the input layer, just like the inputs that we feed our neural network. And then the second layer is called the first hidden layer, which has neurons that are connected to the inputs. Usually it is fully connected, like layer where all the inputs get connected to every neuron in the layer. So all the layers actually in the middle are called hidden layers, and the final layer is called the output layer. So you might have one output or multiple outputs. So this output is a neuron. So we have 3 neurons in the second layer. We have 3 neurons in the first layer. And this creates to us like an artificial neural network or multi-layer perceptron, what we call. So we talked about the weighted equation here, which is basically what we call Z in this case. And the activation function that we're going to use here is the threshold activation function, which is going to give us 1 if the Z, which is the weighted sum, is greater than or equal the threshold. Otherwise, it will give us 0. Okay, so that's activation function. However, as we'll see later, that this activation function is not like useful for training neural networks because we need the activation functions to be differentiable and to be kind of nonlinear so that we can actually pass information from the output backwards to the inputs. So we can actually represent this information by using what's called the bias. Okay, so if we take the threshold to the left in the equation, so the bias becomes the threshold. So the perceptron actual equation becomes the weighted sum plus a bias, and then we compare it to 0. So if it is greater than or equal 0, it becomes 1, otherwise it becomes 0. So a neuron now has the weights and the bias as parameters. These are the ones that we need to learn for whatever function that we would like to design. Now, as I mentioned just a while ago, that the activation function that we would like to use, it has to be nonlinear. And in fact, there are so many choices that we can use. For example, the sigmoid, the tanh, the soft, plus the ReLO, which stands for linear electrifier, as shown here in the graphs. So we usually use one of those in the hidden layers. So the most famous one that is used actually in the hidden layers is the ReLO, okay, because it is computationally efficient and it actually gives good results. Usually, if we have one output, we use a sigmoid because it gives us like a probability of the output. So if it gives us a probability of 0.9, that means, yes, whatever we are classifying is correct with a probability of 0.9, or it is the thing that we would like to detect. And if it is closer to 0, it's less probability. So we use one of these, and you can play with them and experiment and compare the performance, but usually the ReLO does very well, and it is actually, because it's computational efficiency, it is used in the hidden layers. All right, now neural networks, we hear about now, they're called deep neural networks because like depth, we look at now the famous neural networks that are used for image classification, and they have large number of depth. So here the depth is like how many levels, like you go from the input to the output. So this has a depth of 2, for example, and this has a depth of 3. So usually here it says depth greater than 2, but if you look at the practical neural networks, they have a large number of like depth. You might see 20 layers or more of like layers of neurons, hidden layers in the neural network. Now I'm going to show you that we can actually use the neurons to implement Boolean functions. Okay, and we'll start with the simple logical operations like the AND. As we know, the AND will give us like if the inputs are 1 and 0, where 1 stands for true and 0 stands for false, it will give us true or 1 when both inputs are 1. Otherwise, it will give us 0. So if I would like to design a neuron to implement the AND equation or the AND function, I can just set the weights to be 1 here and set the threshold to be greater than or equal the number of basically variables which are not inverted, which in this case we have 2 variables, so the threshold is 2. So you can see that, for example, if I put x equal 1 and y equal 1, now the value of z is going to be equal 2. Is it greater than or equal to? Yes, we're going to get the output as 1. If any one of them is 0, we're going to get the total weighted sum less than 2. So since it is not greater than or equal to, we'll get 0. And you can see that this actually implements an AND function. If I would like to implement an OR function, okay, again, the formula that we use for that, I'm going to show you the general formula. But if I use the threshold equal to 1, this will implement actually the OR gate. For example, you can see if both inputs are 1, we know the OR function will give us 1 if either of the inputs or both of them is 1. Okay, so the only way we get 0 if both inputs are 0. So if you put 1 here and 1, now the weighted sum is going to be 2. Is it greater than or equal 1? Yes, we're going to get 1. If we put 1 and 0, the weighted sum is going to be 1. Is it greater than or equal 1? Yes, we'll get 1. If we put 0, 1, we're going to get 1. Is it greater than or equal 1? Yes, 1. The only way to get 0 is when both inputs are 0. And in this case, the sum will be 0, which is not greater than or equal 1. And we can see that this implements an OR gate. So in fact, we have a general formula for implementing AND gates and OR gates. So this is the formula for implementing AND gates. So it says the threshold that we should use. So here we represent the X bar, which means the inverted input. So we could have the inputs either in true form or inverted form. Okay. So what we're going to do, we'll assign 1 for the non-inverted inputs and -1 for the inverted inputs. Then the threshold will be L, which is the number of non-inverted inputs. So here I have 2 inputs, which are non-inverted, so the threshold will be 2. And this will implement, for example, this AND gate, X1 and X2 and not X3. Similarly, we have a formula for implementing any OR gate with inverted or non-inverted inputs. Again, we put the weights 1 for non-inverted inputs, -1 for inverted inputs. And the formula will be 1 minus, that the threshold should be 1 minus the number of inverted inputs. So in this case, we have 1 inverted input, so the threshold will be 0. So we can implement this way any OR gate. That's why if we go back to this example, we didn't have any inverted inputs, so the threshold is 1 minus 0, which is 1. So if you have any questions, you can ask me, like stop me as I'm going. For implementing the inverter or NOT gate, so again, the weight is -1, so we can consider this like an AND gate. So we have basically number of, we put this as -1. So since this is like a kind of inverted input, like has -1, okay, so the threshold will be 0. Now we have another function that is very important, which is the exclusive OR. And this function should produce for us 1 if either of the input is 1, but not both. In other words, it gives us 1 if the 2 inputs are different from each other. Can we design this using a single perceptron here? And the answer is no. We cannot like actually implement this XOR functionality using only a single perceptron. We need at least 3 perceptrons, or actually 2 perceptrons to do it. We can do it with 2. So we can say that we can model it by saying, okay, the exclusive OR, which is the truth table shown here, is either X or Y and not X or not Y, which means it has to be X or Y, but at least one of them has to be inverted, not both of them to be like 1. So this is one way of representing it. There are other ways. So we can actually go and implement this by using just one neuron to implement the OR equation here, which is this neuron. And we'll say, okay, we have X or Y, so the 2 inputs are not inverted. We put 1, 1. So what is the weight? 1 minus the number of inverted inputs. So since we have 0, so 1 minus 0 is 1. Now for implementing the second OR gate, not X or not Y, so the inputs will have a weight of -1, each one of them, and the equation will be 1 minus 2, because we have two inverted inputs, so the weight, the threshold will be -1. And finally, we implement an AND between this part and this part, so the weights here will be 1, 1, and the threshold will be 2, because we have two non-inverted inputs. So 3 neurons will implement actually the exclusive OR. But this is not the only solution. Neither the solutions for AND OR are the only solutions. We could have other solutions. We could have different weights and different thresholds that will implement actually the AND and the OR. But these like formulas will always work. So it's just like one implementation that will always work, but this is not the only implementation. For example, this is an implementation for the XOR, but this is another implementation for the XOR that actually will give us the correct functionality with just like two neurons or two perceptrons. Now, we would like to show you this example because it's going to give us like very important message, is that we know in Boolean algebra that any Boolean function can be represented as sum of products, okay? We call them each one of this product. What is a product? Is the input combination of the inputs. So we represent this in a truth table. So whenever we write a Boolean function, we represent the conditions that make that function true or 1. So these are all the conditions on the inputs that make the function 1. All other conditions will make it false or 0. So I can represent the equation of y by representing the conditions. So I say y will be 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, x5 is 0. So we represent it by putting a bar whenever it is 0 and non-barred variable or non-inverted variable when it is like 1. Or this is like we use plus for representing the OR. We take the second condition and represent basically its equation or until we represent all the conditions that make y equal 1. Now we know, okay, we can build or implement this equation using a neural network by having one hidden layer where each neuron in the hidden layer will implement one of those AND equations, okay? And then one neuron at the output layer that implements the OR of all of them. So one hidden layer with as many neurons as many terms we have that make the function 1, and finally one neuron at the output that makes it, that implements the OR operation. So this way we can implement any function using just like single hidden layer. But the problem with this, like, okay, here's an example, like we're implementing just like this function where we have two product terms, A and B and D, or not C and D. So as we said, like for non-inverted variable, we put the weight as 1. The AND will be the number of non-inverted variables, which is 3. For second AND gate, we have not C bar or not C and D. So the inverted variable gets -1. The non-inverted gets 1. The threshold will be the number of non-inverted, which is 1. And here we're implementing basically the OR operation, putting the weights 1, 1, and it is 1 minus the number of inverted inputs, which is 0, so that this implements basically the equation. Now, the problem with like implementing functions like this is that we might get exponential number of terms that make the function 1. And this happens actually in particular for the exclusive OR function. So the exclusive OR function is actually known as the odd parity function. So it gives us 1 when the number of ones is odd, and it gives us 0 otherwise. So if you look at actually the equation of that, we will have exponential number of terms. So if I have 10 inputs, the total number of terms will be 2 to the power 10, which is 1024. Half of them will give me 1 and half of them will be 0. Half of them odd, half of them even. If we're talking about 20 inputs, you're talking about 2 to the power 20, which is like around 1 million. If you have 30 inputs, you're talking about 1 billion. So you will end up with having a huge like networks to represent such OR gates. However, we will see next that if we actually implement this in a multi-level structure, so each, like we have seen that 3 neurons here can implement the XOR. So I can say, okay, if I want to implement an XOR function with 6 variables, I can implement it in a multi-level like this. So here, the first structure here implements X1, X-exclusive or X2, and then the result is XORed with X3 using another structure, and then the result of that XORed with X4 and the result with x5 and the result of x6. So the number of exclusive OR operations I need is the number of variables minus 1. And this shows me like how many levels and how many neurons I need. So if we look at this, how many neurons we need, okay, we had 5 XOR gates, and in each XOR gate we have 3, so we get 15 neurons. If we compare this with just using one hidden layer, now how many conditions do we have that will make the function 1? We said half of them. So it's gonna be 2 to the power 5, which is 32 conditions. That means we will need 32 neurons in the hidden layer and 1 neuron in the output layer. However, if I use multi-levels, I reduce significantly the number of neurons. And if I reduce the number of neurons, I'm gonna reduce the network parameters, which are the parameters that need to be learned when we train it. So this example shows us that more depth can reduce actually the network parameters that are needed to implement the function. So that's why we need, when we design our network, we should have sufficient depth so that we get like better optimizations of the number of parameters that need to be learned in our network. Okay, so this is actually the intention of this example, to show you that if you just like use small depth, you might end up with having larger number of neurons to be able to approximate or represent your function that you would like to represent. But if you have more depth, you will end up with less number of neurons and less parameters to learn. So we have seen that a multi-layer perceptron can represent a given function only if it is sufficiently wide and sufficiently deep. So for example, if I'm talking about the exclusive OR gate here, the exclusive OR gate, and we said if we have 6 inputs, we said we need 32 neurons in one hidden layer, if we're gonna use one hidden layer. So if you use less than 32, you will not be able to correctly basically represent that or learn that network. So you need at least 32 neurons in the hidden layer and then 1 in the output layer. So if you don't have sufficient breadth, you will not be able to learn. Now, if you don't have sufficient breadth, you need more depth to be able to learn. So this is basically what we're saying. A network with fewer than the minimum required number of neurons will not model the function. So optimal width and depth will depend on the number of variables and the complexity of the Boolean function to find what is the best really trade-off to minimize your parameters. But more depth will reduce the number of parameters that you need to learn. But it might create problems, like more depth, it might create problems in the learning process. This is why you need to compromise. Okay. So as we have said, deeper networks may require far fewer neurons than shallower networks to express the same function, as we have seen with the exclusive OR functions. And we have seen that the networks that require an exponential number of neurons, okay, will require an exponential number of weights, and to reduce that, we need more depth. All right, so this is about like how we can use, we have seen that actually a neural network can represent any Boolean function because we can just express it as a sum of products, where each product is represented by a neuron, like to implement the AND operation, and then a final neuron to do the OR operation. Now we'll see that we can actually use neural networks as universal classifiers. Okay, so this is our neuron that we have. This is the equation. We can actually build a neural network such that we give it an image like this, 28 by 28 image, for example, representing the pixel intensities. We can convert this into one vector, and that one vector will feed basically our neural network. And then we can have as many hidden layers as we want. And finally, we'll have one output that will tell us, for example, is this 2, does this image represent the number 2 or not 2? So this is just like one output neural network that has 784 inputs, which is the result of multiplying 28 by 28 and making it one-dimensional vector. And the result will be 1 or 0. 1 means, yeah, the image represents 2. 0 means it's not 2. So this is like one classification problem that we might want to design. Now we'll see actually that the perceptron, you have seen the perceptron algorithm in the morning session. So the perceptron algorithm actually is a linear classifier, as we have seen in the morning session. So we have the weights W1 multiplied by X1 plus W2 multiplied by X2 equal threshold. This is the equation of the line, or -2 equals 0, where we have the bias. So in fact, this is the equation of the line, and we say, okay, if it is greater than or equal 0, or greater than or equal threshold in this case, it means it is in this side, or this is a decision boundary you want. Otherwise, it will be 0. So it is a linear classifier. We could say anything above the line is 1, anything below the line 0. Or we could say anything below the line is 1, anything above the line 0. We can choose whatever like area we want to detect, and we can actually have the perceptron do that for us. We'll show an example. For example, the OR function that we have seen, we have 4 values only. So we can take a decision boundary anywhere here, and we say that anything above the line give us 1. So whenever we have 1 in any of the inputs, we get 1. Now for the XOR, we can see from the picture here why a single perceptron is not sufficient, because we need to say only 2 points will produce a 1. When it is 0, 1 or 1, 0, but not 1, 1, not 0, 0. So say when it is above this line and below this line. So we just need 2 decision boundaries to detect the XOR, above this line and below this line. So this is like how we should detect the XOR. We cannot do it with a single decision boundary to detect the XOR operation. Now, as an example, like let's say we have this line boundary, and we would like to detect points below this line to be equal 1, to be labeled 1, and points above this line to be labeled 0. And this is the equation of the perceptron that we use, where we use a bias. So what we say, we need to find first the equation of the line. So you take 2 points that the line passes through and find the equation of the line. Compute the slope, compute the intercept, and you get the equation of the line. So this is the equation of the line, that x2 equal -2x1 minus 2. And now we'll form the decision boundary. Where is my decision boundary? I would like to detect points below the line. So we'll say, okay, my decision boundary is that x2 should be less than or equal -2x1 minus 2. Meaning that any points below this line will be 1, otherwise it will be 0. And then we take this equation, we have to rearrange it in this form, greater than or equal 0. Once we rearrange it, we get actually the values of the weights and bias. So we say weight 1 is -2, weight 2 is -1, and the bias is -2. So then we find actually the perceptron parameters that will detect decision boundary. Now, if I give it any point in this region, it's going to produce for me 1. If I give it any point in this region, it's going to produce for me 0. If I wanted to detect the points here above the line, it's the same thing, except that now the equation will be greater than x2 greater than or equal -2x1 minus 2. I will rearrange it in this form. I'll find what are the weights and the bias. So one perceptron will give you 1 decision boundary. So now we give this example. Let's say we would like to detect things inside this decision boundary. So we have this shape, and we would like to detect all the points inside the shape should be classified as 1. All the points outside the given shape should be classified as 0. So we'll say, well, we have how many decision boundaries? We have 1, 2, 3, 4, 5. So for each one of those decision boundaries, we're going to use 1 perceptron. So 1 perceptron to say, okay, I would like to detect things that are greater than or equal this point. So let's go with the illustration we have. So 1 decision boundary, 1 perceptron here is going to detect points above this line. Then we'll use another decision boundary to detect the points above this line. So now we have 2 perceptron, 1 detecting above this line and 1 detecting above this line. And then a 3rd boundary to detect points below this line. A 4th boundary to detect points below this line. And then a 5th boundary to detect points above this line. So we have now 5 neurons, each one of them detecting a certain decision boundary. And then I need an AND, basically a neuron to compute the AND function to say, I'm gonna produce 1 if all of them produce 1. So we will use here the threshold of equal 5. So you can see that the regions with the numbers like put in this, and you can see that we can actually detect this way all the decision boundaries inside the shape. And then we, for an interesting thing, we tell the students, what if instead of using an AND gate, what if we made the threshold here equal 4? What are we gonna detect? What shape we will detect, or this neural network will detect? So you can see that the points that have 4 or more are here like the star shape. So if I just like put here 4 instead of 5 in the threshold, it's going to give me 1 whenever the points inside the star. Otherwise, it will give me 0. If I put 5 as the threshold, it's going to give me that shape here, and so on. Now we'll say, well, if I want to detect like a more complex object, like here we have 2 objects, it's very simple. Because what I can do, I can say I have 2 objects, the upper object and the lower object. I can design a neural net here for the lower object, like 1 neuron for each decision boundary. I have 5 decision boundaries, so 5 neurons, and then an AND gate. And then another neural network here, I have 5 decision boundaries, 5 neurons, and an AND gate. And then I will say, okay, I'm going to produce one if the points are inside this shape or inside this shape. So I'll use 1 neuron to implement the OR function. So it's going to give me 1 if it is inside this shape or this shape. Now we can apply the same principle for any complex shape that we have. We just have to decompose it into objects that can be detected individually and then just like do the OR operation. So we have, for example, this part, 4 boundaries, 4 neurons with an AND gate. This part, 4 boundaries, 4 neurons with an AND gate, 4 neurons with an AND gate, and so on. And then eventually OR to detect basically all the objects inside that shape. So now here's an example that we show the students so that they can compute the equation of the line, arrange the equations, and then compute the weights. So we tell them, okay, design a neural network to compute basically points inside this shape, the yellow shape. So they go and find, okay, there's a decision boundary. So they find the equation of the line. They say the equation of the line is x2 equal x1 plus 1. Now I want to detect points below that line. So they say x2 should be less than or equal x1 plus 1. Now rearrange that equation to be in the form greater than or equal 0. They will get this equation. So they will deduce now that weight 2 should be minus 1, weight 1 should be 1, and the bias should be 1. So this is like the part for detecting this decision boundary. Now they go for this decision boundary. Similarly, they find the equation of the line. Now the decision boundary should be 1 when x2 greater than or equal minus x1 minus 1 above the line. Okay, rearrange it to be in the form greater than or equal 0. You get the weight should be like W2 should be 1, W1 should be 1, and the bias should be 1. And do the same thing for the other boundaries. So now you have found the weights for the hidden layer, and then you just need an AND gate to implement basically the AND operation. Since we are using bias, bias will be minus 4 since the threshold will be 4. Bias is always minus the threshold. And now they have designed a neural network to detect basically objects inside this shape. So this is the end of the first part. If anybody has questions, I can answer it, and then we can move to the second part. No questions?
Thank you, Dr. Ayman. Just a quick probably comment or clarification. So the students, after being able to develop this, the schematic of the new neural network, how would they apply it in Python, or will they not in this course?
They do, actually. In fact, the programming assignment I'm going to show you that we gave them an object. We tell them design a neural network to detect things in the object. Now verify your design. So they will verify it and show that they get 100% accuracy. And they we'll tell them take that neural network and train it now and measure the accuracy through training. So they do it by design, and then they try to solve the problem by training. I'm going to show you the example in the notebook, but after I cover part 2.
Yeah, Dr.
Great,
Ayman,
thank you.
Question, please.
Pardon.
Yeah, here the first hidden layer perceptrons. The logic operation there is what, and or what?
No, here in the first layer, they are not like logic operations. They are decision boundaries.
Yeah.
In the second layer, the output layer here, it is an AND gate. But for example, if we go back, like the first layer, each one of them is just detecting a decision boundary. Then the second layer, all of them are AND gate. And the third layer here is an OR gate. But the first layer, each one is detecting a decision boundary. Are the points above this line or below this line? Are the points above this line? So each perceptor neuron is a decision boundary detector.
I have a question about the AND and OR gate representation. So what's the difference? Is it the bias? Is one for OR and
The
minus
threshold, yeah, the threshold will make it implement an AND or an OR.
But what values did you use for the input, X1 and X2? When
No,
you were
it can, I mean, if you're implementing AND operations or OR operations, let me go to this example. You assume that the inputs will be 0 and 1, right? Because this is Boolean function, so the values have to be either 0 or 1.
okay.
Okay, other questions?
Dr. Ayman, there was a question on the chat.
Yeah, I'm not seeing the chat.
Yeah, the question says, does this MLP work when the data is not linearly separable?
Yes,
I have
absolutely.
answered in one single phrase, but if you can elaborate on this.
Yeah, this is the beauty of neural networks. In fact, they can detect nonlinear boundaries very easily. Multiple classes, classifications, so there is no problem at all. They will detect. However, we have to use the activation functions to be nonlinear for them to do that.
And the MLP has to have sufficient structure.
Yes, as I illustrated, if you must have sufficient depth and breadth to be able to approximate function. But neural network can do anything, can approximate logic functions, can approximate continuous functions. They can detect shapes, whatever that shape complex. As you can see, you just have to decompose it into smaller parts and then detect each part separately and just like do the ORing. So what we have seen so far is that neural networks are capable.
I have one more
anything.
question.
Yes.
Can you comment on the historical confusion of the XOR? Why it was thought not possible to be made with one layer? I mean, it's not clearly you need 2 layers to do it.
You can see it from here, from this graph here. The XOR should give you 1 when the 2 inputs are different from each other.
But why did people miss it? Because you make it sound so easy.
What do you mean miss it?
Why people missed the fact that XOR could be represented by 2 layers?
They did not miss. They just said that it cannot be represented by 1 perceptron, and this is always true. It cannot be modeled by 1 perceptron. But you need to do it with at least 2 perceptrons. So this is like, as I showed you in the example, they did it with 2 perceptrons. Like here, for example, with 2 perceptrons, they were able to do it. So it's not like the AND OR trivial. This is like AND OR, but this is like with using special weights and so on. So it was designed with just 2%. So the minimum is 2 to be able to do the XOR.
Okay, clear. Thank you.
Okay, so the summary of this unit, we have seen that neural networks could represent any Boolean function. They could actually detect any shape or points inside the shape. There's one part that I didn't show you, that they can actually implement any continuous function. So they are capable. Like if we have sufficient structure, they can actually model whatever we want. Now, in the second part, I'm going to show you now, how can we train them actually to learn? For example, detecting points inside such a decision boundary, classify points which are not linearly separable, and all this it does. So we look at the learning process. So I'll stop sharing and then share the second part. Can you see the second presentation?
Yes.
Okay, in this part, we will define the neural network learning problem and what is the setup, how we can make it learn, and what do we need to learn in particular. And then we'll see that actually the learning process is very simple using the gradient descent algorithm. And we'll show you, like, if you're not familiar with the gradient descent, like what is the idea behind it, and then how we can use the gradient descent algorithm to train neural networks, and variations of the training algorithms, and finally, how we could avoid overfitting during neural network training. So this is like the neural network structure. We just say the first layer is the input layer. I would like to emphasize that the input layer has no neurons, just like the inputs, but just like for convention, it's called a layer, the input layer. And then the first layer is the one that has the neurons, and second layer and so on. All the layers in the middle are hidden layers. And finally, we have an output layer that could have one or as many outputs as desired. Okay, so we have seen that the neural network can model any Boolean function, they can classify any decision boundary, and they can also classify or model any continuous valued function that I haven't showed you, but has been proven. So neural networks, basically architecture, when you design a neural network, you need to determine the number of layers in the network, like how many layers and how many neurons in each layer. So one class of neural networks is called feed-forward neural networks, which has no loops. So every layer just connects to a subsequent layer, so we don't have feedback. However, we have a class of neural networks that actually have feedback, which is called recurrent neural networks. We don't cover it in this course. They get covered like in the deep learning course, but they are also very interesting whenever you want to detect sequences and have like kind of time into it. But here we just like focus on feed-forward neural networks. They are called actually fully connected neural networks, where all the inputs are connected to all the neurons in the subsequent layer. And then all the neurons in the first hidden layer are fully connected to a second set of neurons, the second layer, and so on. So the neural network parameters that we need to learn are the weights and biases in the network. So for each neuron, if we are talking about fully connected layer, and we have, for example, 10 inputs, then we have 10 weights for each neuron and one bias. So if I have, for example, 10 inputs and 5 neurons, we're talking about how many weights? 10 times 5, 50 weights plus 5 biases, because each neuron has a bias. So these are the parameters that we need to learn. So you can easily see that the more layers you add and the more like number of neurons in each layer, you can easily get into like large number of weights that need to be learned. So the neural network problem, learning problem, is basically involved with determining the values of those network parameters, the weights and biases, such that it computes the desired function. So we need, whenever like we have data that we would like to model, we have a training data that is labeled. So neural networks here are used as supervised learning techniques, where we have labeled data. So I have a desired value for my input sample, and I'm gonna compute what the neural network produces to me, and then compute an error, which is by comparing based on the difference between the desired value and the produced value. So the overall goal of training a neural network is that we would like to model or approximate some function gx like this. Okay, so we're given some function that we would like to model, and we would like to find the weights and biases such that the function produced by our neural network, which is fxw, so based on the weights, it actually approximates the whatever produced by gx, or give us like very similar or with minimum number of like error. So we go and build the network, and then we try to learn the weights and biases, and we keep adjusting them to minimize the error function, okay? So we need to minimize the error function. So in order to approximate that function and be successful, we need sufficient data sampled statistically well so that we will able to actually predict it. If the data like provided the neural network is not sufficiently spanning the function that we will model, will not be able to model it accurately. So more training samples more like good training, like statistical distribution of samples will give us better results. So what we do, we'll get some training samples. We call them XI here. For each training sample, we have a desired value, which is what the function GX actually compute. And then we'll take these values and feed them to the neural network. And based on these values, we're going to learn like the weights that minimize the error between what the desired value is and what actually my neural network produces. So this is actually our problem. So we're going to get basically a set of training samples, training samples, X1, X2, Xn, and for each training sample, the desired value. X1 here doesn't represent one value, it's a vector like of the number of inputs that we need. So just reference to one training sample that has a number of like inputs, and we have a desired value. Again, the desired value could be like a vector, not necessarily one value. So we have a set of training samples, like input sample with desired value, input sample, desired value, that we're going to use to actually train the model and find what are the best weights and biases that will minimize the error for approximating our function, for example, GX. Okay, so mathematically, this can be modeled like this, that the weights would like to find the argument of weights that minimizes the divergence over all the inputs, the divergence between what my neural network produces and what actually is desired, what is the actual values. So this is like mathematically how we represent it, but in short, we would like to minimize the error for not only for the training samples, but for any basically sample that not seen. We would like to find what are the best weights that minimize the divergence between what I desire to approximate and what my network actually produces. So we need to use a divergence function. So we call it divergence function, but this represents the error function that can be used. And one of the divergence functions that can be used is the squared Euclidean distance, okay, which is modeled like that. And the reason we have half, because as we'll see later, when we take the derivative, we want to cancel the half. So it's just like the difference between what the network produces minus the desired value squared, and we take the sum and then we divide by 2. Now, it's very important during the learning process that the divergence function to be what they call it, for optimizations, it has to be a convex shape like problem so that it allows it to optimize the error, reduce the error as fast as possible, and it allows it to converge. All right, this is just like really for notation. We use some notation so that we can follow. So we said that our network will be structured in that manner, okay? The input layer has no neurons. All the intermediate layers are hidden layers, and the final layer is the output layer. And we use some notation here. Like, for example, each output in a given layer is given like a superscript to represent the layer number. So for example, we call this, although it's input for consistency of notation, we call it Y1 superscript 0 because layer. This is Y2 superscript 0 and Y3 superscript 0. Now in layer 1, we call this also Y1 superscript 1, which means the first output in the hidden layer 1, second output in hidden layer 1, and so on. So all the outputs are called Y. We differentiate between them by the superscript. So this is YI superscript 0, superscript 1. So the superscript represents the layer, okay? And also we represent the weights, like, for example, weight ij, it means this is the weight connecting neuron I in the previous layer with neuron j in layer 1. So the weights that are connecting to layer 1. So the superscript here represents layer 1 that we are connecting to. And this means we are connecting basically input I to output j, or basically the input here I to j. We'll show here some examples for illustration. For example, if we look at W21 superscript 2, this is like what is shown here because we are talking about layer 2. So this is layer 1, layer 2 from the superscript. And this is connecting the second basically node in layer 1, which is the previous layer, to node 1 in that layer. So this is W210. For example, Y20 represents basically the blue. This is Y2, the second node in the first layer. That's why the first layer is 0. So this is second node, so this represents the blue line. Y14 is shown in brown, okay, which is this one. So it is the first output in layer 4, okay, and so on. So now our problem can be formulated as follows. So we have the xn here represents the nth input vector, okay? So that vector could have d dimensions or d values. And dn is the nth desired vector values, okay? Again, we could have any number of like outputs depending on how many neurons we have the output. Here we assume we have L, okay? And similarly, this will be what our network will produce. So this is like the notation. Now, how we represent the values when we are like classifying methods. So usually, as we will see, for example, if it's binary classification, it will be easy, like 1 or 0. For example, cat means 1, no cat means 0. For multiple class output, usually we use the one-hot representation. So 1, 0, 0 represent that the object we are classifying, it is the first one. 0, 1, 0, it is the second object, and 0, 0, 1 is the third object. So this is usually the representation that is used for multi-class output problem. So now we can say what we need to do, given basically the training samples and their desired values, we know and given the divergence function that we're going to use, like the Euclidean distance, for example, we would like to minimize the error, the average error, over all the training samples. So we need to train our neural network by finding the divergence between what the network produces and the desired value over all the training samples and take the average. And we need to keep iterating during the learning process until we minimize this error. So this is actually how the learning process. We'll keep adjusting the weights and biases and keep computing the error until basically the error reaches to a very small value, or like the difference between the error from one iteration to another, it becomes less than a certain threshold, then we stop the learning process. This is just like a simple network that has 2 hidden layers and 1 output, and this is like the divergence function with the desired value and the output value. Now notice that here, like the bias is considered as an extra input, with like we having 1 for the input. So I mean, it can be represented this way, or it could be shown as an arrow with the summation. Now each neural network has activation function. Each neuron has activation function. So usually what's done is that each layer has the same activation function. So we don't use like for each neuron a separate activation. So I might say, well, I want to use sigmoid for the first layer. I might use tan-H for second layer, and so on. So we choose like the activation functions per layer. All right, now let's go and see how can we train the neural networks to actually minimize this error. In fact, it's actually very simple. Let's think that we have just one parameter that would like to actually learn, which is x here, and we have the error function as y. And let's assume that this is actually the error function. So what we need to do, we need to compute the slope, which is the derivative of y with respect to x. Now we look at the slope. If the slope is positive, what shall we do with that x, our parameter? We know that to minimize the error, we need to reduce x. Suppose the parameter was here, we will compute the slope and find the slope negative. We will say, okay, we need to increase x to minimize the error. So either we have to decrease x or increase x. And how can we do that? By simply just computing the derivative of the error function with respect to our parameter that we would like to learn. So this is actually the problem that we need to use. Now, this can be solved mathematically to find, well, we know that there's like math people are expert. They can say, well, we can solve this. However, when you talk about neural networks that have millions of parameters, this becomes intractable. So we cannot like solve it mathematically and come with a closed form solution. It will be very computationally expensive and so on. So what we do, we're going to use iterative techniques to solve this problem. And what we'll do, we'll use what's known as the gradient descent. So we're going to start with an initial point and then find like, okay, whether we need to increase the weight or decrease the weight by computing the gradient, the derivative, I mean, and then either increase basically that parameter or decrease it, and then recompute and keep doing that until basically the error is minimized. So for example, I might start at this point, okay, and I compute the slope, I'll find the slope negative, so I have to increase that. I come to that point, compute the slope, I have to increase, come to that point, compute the slope, I find it like positive, I have to decrease until I converge. So you do a solution iteratively until you reach to the minimum or close to the minimum, and the same for basically multidimensional functions. So the gradient descent algorithm for minimizing the error or the loss when training neural networks, it starts with a random choice of weights. Although this is not the best choice, there are people came up with techniques to initialize the weights such that to help the neural networks learning to converge faster. But we can start with basically some random choice of weights and then repeat. We calculate the gradient based on all data points, okay? And then the direction that will lead to decreasing the loss, okay? We're gonna update basically so the gradient will tell us what is the direction that's gonna lead to decreasing the loss, depending on the slope. And then we're gonna update the weights according to the computed gradient. So if the slope is positive, we'll decrease. If the slope is negative, we'll increase. So this is really what the gradient descent is doing. Now, the gradient descent will work if we have convex functions, where we have like basically global minimum 1. But if you have functions that are not convex, you might get stuck in a local minima depending on where you start. So if I start here, I get stuck in a local minima. If I start here, I'll get stuck in this local minima while the global minima is here, okay? So this is like a kind of formulation of the algorithm. You start with iteration 0 with the initial point, and then you compute what is the function for the next value of x minus the function for the current value. If the difference is greater than epsilon, then you compute. So you use this equation to update basically the variable. So this is the value at the current iteration minus the learning rate, and that learning rate could change over iterations. It doesn't have to be constant, multiplied by the derivative. Notice that this equation actually does what we have just said. If we get a derivative that is positive, what do? We said we want to decrease x. So if the derivative is positive, you see you're decreasing x by a factor, which is the learning rate. If the derivative is negative, we said we want to increase x. So you can see negative multiplied by minus, it becomes increase. So this takes care of like what you should do, increase or decrease according to the derivative. The difference is just like by how much. Do you want to decrease it or increase it quickly, or like you want to like take it slowly and so on. But this is really the gradient descent algorithm. Now, here's an example of a function that, let's say, we'd like to minimize it using the gradient descent algorithm that has 3 variables, x1, x2, x3. So suppose we started at the point 111, and we are using the learning rate of 0.3. So what we do, we go compute the derivative of the function with respect to x1, okay, and then substitute the value 111. This gives us a derivative 2. So now we say, well, x1 will be updated as x1 minus the learning rate times the derivative. So it's going to be 1 minus 0.3 times, what is the derivative? 2. So 1 minus 0.6 is going to be 0.4. And the same thing for the derivative with respect to x2 with x3. So from 111, the next point will be 0.4, 1.4. And in fact, if we repeat this iteratively, as shown in the Excel sheet here, we end up into minus 0.98, minus 1.02, minus 0.98. The minimum actually happens with minus 1, minus 1, minus 1. So now because the learning rate is 0.3, you see you keep oscillating here around the point. That's why you start with the larger value of the learning rate, and then you decrease it as you go on so that you can converge and reach to the actual global minimum. Any questions so far? Okay, now we just like to talk briefly about the convergence of the gradient descent. If the function is convex, it will converge and will reach to the global minima. But if it is not convex, it will be stuck in a local minimum. or deflecting point. So what we should do when we choose our error function, we should make sure that it is actually a convex function so that we help it, the learning process, to reach to the global minimum. Now, this actually heavily depends on the learning rate. It can be proven that we can reach to the minimum within one step. And that's called the optimal learning step. So for any function, you could actually compute what is the optimal learning step that take you from any point to the minimum. Now, if we use the optimal learning step, it's going to reach within one step, one iteration, we will go to the minimum. To the one update will take us to the minimum. If we use a learning rate less than that basically value that take us to the minimum, we're gonna it's gonna smoothly take several steps until it basically converges, but it will converge. If we use a value between the optimal learning rate and less than twice the optimal learning rate, okay, what it will do, it will oscillate, but eventually it will converge. If we use a learning rate greater than twice the optimal, then it will diverge. Now, the challenge here is that the learning rate for each weight, the optimal learning rate for each parameter is different. So they do not have the same optimal learning rates. And this is what makes basically the learning. So maybe it will oscillate for one parameter, maybe it will converge slowly for another, maybe it will diverge. So this is a challenge, like how to choose the learning rate. So, but usually what is done, it is like done through the experimentation, where you start with a kind of slightly higher learning rate, and then you decrease it like as you go with the training process, and usually this produces good results. All right, now, just like summary of the perceptron, we said we have, this is our perceptron, which is a weighted sum, and then feeding an activation function that produces the output. We can look at this, which has a bias, or we can think of the bias as an extra, basically input, an extra weight, where the input is 1. So our problem that we would like now to solve is that we might get like images, which, for example, we would like to build a neural network to detect whether this is like a certain, let's say, digit 2 or not digit 2. Then we'll have one output. So, for example, image of 5, that's not a digit 2, so the desired output will be 0. Image of 2, that's the desired output, is 1. And all images of 2 will give us 1. All images of non-2 will give us 0. So in this case, I will have a single output. This is like one binary classification problem. Now, the other problem is where I have multi-class classification problem, where I have multiple. So I give it images of digits from 0 to 9, and I would like to detect it. So I give it the image of 5, it tells me 5. The image of 2 is 2, and so on. So in that case, I need to have 10 outputs in the output layer. And the activation function that we're going to use is called softmax, which actually computes a probability for each output, such that the sum of the probabilities will be 1. So the output with the highest probability will be the one that will be classified to, and the one with the lowest probability, I mean, all the others will be considered as these are not the correct classifications. Sometimes people look at not only the top value, but the top, for example, 3 or top 5 objects that have been classified, especially when you have a large number of classes. For example, let's say you're classifying images of 1,000 different objects. So you have like 1,000 outputs. So you look at the top, for example, 3 or top 5 and top 1 to compare the performance of neural network. So when I train a neural network, I'm going to have my neural network here. Let's say I have 4 outputs. I'm going to use the divergence function. So here we're using the what's called L2 divergence, which is the Euclidean distance. I'm going to feed it with the desired value. So for every training sample, I'll feed it with the desired values. Now, notice that we said we need to compute the gradient, which is the derivative of the divergence function with respect to each network parameter, with respect to each weight and each bias in the network. So what we have to do, we'll compute the divergence function, and then to adjust the parameters, we are going to compute the derivatives with respect to this divergence function with respect to each parameter in the neural network, and then adjust each parameter accordingly. Okay, so the derivative of squared Euclidean distance here is simply for each output is going to be yi minus di. So it's going to be trivial. Okay, if we take the derivative with respect to each output, with respect to y1, it's going to be y1 minus d1. With respect to y2, it's going to be y2 minus d2, and so on. So what we're going to do, actually, we'll compute the derivative using the chain rule. So to compute the derivative with respect to this weight, I have to compute the derivative with respect to this output, and then multiply it by the derivative of this output with respect to the derivative with respect to that weight. And even for here, I'll have to do it using the chain rule, going this way, this way, this way, this way, until I reach to the basically the layer or the weight I would like to compute the derivative for it. So this is actually the process of how we are going to train the neural networks. Basically, we need to do forward computation, compute the desired, what are the outputs predicted or produced by neural network, compute the divergence functions based on comparing them with the desired values. Then we call this forward computation. And then we're going to do backward computation by computing derivatives of the divergence function with respect to each parameter in the network and adjust it and repeat the process and so on until basically we converge. So this is an illustration of just the chain rule. So this is why the activation functions need to be differentiable. If they're not differentiable, we will not be able to learn because we will not be able to pass backward, propagate the derivatives and so on. So we'll not be able to adjust the weights. So activation functions must be differentiable. So in this case, if I would like to compute what is the derivative of y, for example, with respect to a certain weight, I'll say, well, it is derivative of y with respect to weight I. It is, by chain rule, it is the derivative of y with respect to dz, which is the derivative of the activation function, multiplied by derivative of z with respect to the particular weight that I want, which is weight I. Now notice that the derivative of z with respect to weight 1 is nothing but x1. Derivative of z with respect to weight 2, nothing but x2. Derivative of z with respect to weight 3, x3, and so on. So this way I can find the derivatives, multiply them, and then compute how the weights should be adjusted using the formula that we have seen in the gradient descent. Okay. Now, if we have deep neural networks, you're going to multiply derivatives, multiply by derivatives, multiply. So you might end up in getting like what's called the vanishing gradient. Okay, where the gradients become very small, so their effect becomes like negligible and you're not able to adjust the weights. So people took care of the vanishing gradients by choosing proper activation functions and in adjusting the structure of the neural network to try to minimize the impact of the vanishing gradient. All right, now we'll see the algorithm that we can use for training neural networks. So this is the error function that we're going to compute. T is the number of input samples or training samples. D is the desired outputs for training sample I, Di, and Yi is the output produced by neural network for training sample I. And here is the first algorithm that we will actually go, which is training neural net using gradient descent. So how it works, we're going to initialize our weights and biases, like either randomly or using basically initialization technique. And then we're going to repeat until the error converges. Okay, so we'll compute basically the error. So in this algorithm, we're going to go over all the training samples and then update the weights once. And then go, like if the error hasn't converged, go again over all the training samples and update the weight once, and so on. Yes, Dr. Anas, you can ask if you have questions.
Yeah, thank you, Dr. Ayman. How to decide on the value of the error?
The error is based on the divergence function you choose. For example, Euclidean distance is one of them.
Yeah.
There are others that give better results than the Euclidean distance. So there are many. So you choose, like there are, as I'm going to show you in the notebooks, what is used. So there are like other ones, but we don't, for here, for this level, of course, we just cover the Euclidean distance as an example.
Thank you.
So what you do in each iteration, you initialize the error to 0. And then you initialize also the derivative of the error with all the weights to be 0 for all the layers, for all the connections. And then what you're going to do, you will go over one loop here for over all the training samples. you do forward computation, which is computing what are the outputs produced by this network. So you go forward simulation across all the hidden layers, across all the new neurons, until you reach the output, just like simple equation calculations. And then you compute the error. You say the error is so far the current error, which is initially 0, plus the divergence function, which is computed based on what our network produced and what is the desired value. Okay. Then what we do, after we did the forward pass, we compute the backward pass. Now we're gonna go and do the backward computation, compute the derivative of the divergence function with respect to each weight using the chain rule. So we'll go and do backward keep for each weight, compute it by doing this backward, using the simple chain rule for doing that. And then update the derivative of the error with respect to that weight by adding the current derivative plus whatever we have computed using this backward propagation. So this is like the backward propagation. We just went and computed the derivative and updated it. Okay, this is for training sample 1. Now we'll go for training sample 2. Apply it as to the input, compute what is the output, compute the error for that training sample, and accumulate it with the error. Now go for that training sample, compute backward propagation, compute the derivative of the error divergence function with that output produced for the second training sample with the desired output. Okay, back propagate it to all the weights and then update the derivative for the weights. And we repeat this for all the training samples. So if I have 1,000 training sample, I'm gonna do that 1,000 times. Once I'm finished, now I will do the update of the weights. So I'm gonna use the gradient descent update formula. By here you see the weight minus the learning rate times the accumulated error. But I divide it by t so that I compute the average accumulated error. And I do one update. Now I check, has the error converged? No, I'm gonna repeat the process again. So I will go over again all the training sample one more time and do forward, backward for all the training samples, and then update the weights once. And the third training sample, the third round for over training samples. So we call each round an epoch. This is a term that is used actually in neural network training. So you might tell it, okay, train my neural network for 100 epochs. So it will go 100 rounds and update. But you can see, well, is it gonna converge if I give it like 100 epochs like this? It's gonna update only 100 times. It doesn't seem to be like sufficient really to train a neural network. So this is like, yeah, one extreme of doing it. And people thought, oh, well, why don't we go to the other? So just like before I go to the other, just summarize the process. So what we do for each training sample, we do forward computation to compute what is the produced values by our network. And then we do backward computation by computing the error divergence and propagate it back to the weights. And we repeat this for all the training samples, and then we update the weights once. But the problem with this is that I'm gonna do one update for the network parameters for all the training samples. What if my training sample is 100,000? I'm gonna do computations for 100,000 samples and just do one update to the parameters. So it's gonna take me a lot of time really to converge. So the other way to do it is, well, why don't we update per training sample? Why shall I wait by going over all the training sample and update? And that's called the stochastic gradient descent, where I'm gonna update per training sample. Okay, so I'll come over training samples, I'll do forward computation, compute the output produced by my network, compute the error, and then do backward computation, compute the derivatives, and then update. Come to the second sample, do the same thing. Third sample, so if I have 1,000 sample, I'm gonna do 1,000 updates, okay? But the problem with this, it could create issues, like in terms of like, maybe one is doing something, the other one is undoing, if you follow the same order every time. So what we do, every iteration or every epoch, we randomly permute the training samples. So they are basically used in different order every round, and this helps it actually to avoid issues that might happen of doing and undoing basically tasks. This is called the stochastic gradient descent. So this is the other extreme. I am updating every training sample. The normal algorithm called batch gradient descent, I'm updating once for all the training samples. So what is the compromise? The compromise is to use what's called mini batch gradient descent, instead of updating every training sample or updating once for all the training sample, I choose the batch size as a parameter. So I tell the neural network learning algorithm that I want to do update every 64, for example, samples, or every 32. So that could be like a parameter that you could actually tune during the learning process. So then every 32 samples, I update once, every 32 samples. And this is actually what is used in practice because it is the compromise and it is efficient and it helps the network actually converges fast. So this is a mini batch gradient descent. And now what type of optimizers? There are actually people have done a lot of work on algorithms that it help us to optimize the error and reach, like it make it converge faster, like using second derivatives, for example, not only the first derivative. So there is the momentum algorithm, Nesterov accelerated gradient, RMS, probe, ADA-grad, and so on. The most popular one is a technique called ADAM, which actually does very well. All right, I think we reached to 1 hour and 15. We'll stop here. I'm gonna show you after we take a break, like a demo to show you really how neural networks will learn through that demo. And then we will go to, I'll show you some notebooks actually, and then we'll go to the third part, inshallah, which is covering convolution neural network. If anybody would like to ask me now, I'll be happy to answer.
Thank you, Dr. Ayman. A quick question regarding the structure. Is there any kind of guideline or to select the structure in terms of how many hidden layers, what is the depth of each layer? Or is it done like randomly?
It's a very good question. Actually, it's not science. It's just like based on experience, like people try. That's why what people do, they use what's called transfer learning. So if you have a problem that you would like to solve, you don't start from scratch. You take one of the existing neural network structures that have been used to solve some problems, and you start with it. Even use the same weights and so on, and then you train it for your problem, and usually it gives good results. So it's like people, there is no really science to say 5 layers is better than 6 or 10 is better than 5. Depending on the problem that you want to solve, like, and intuition, what is it that you want to try to detect in each layer and so on. So people just like trying. A lot of the work is just really running computations, experimentation, say, well, we get better results.
Okay. Sounds good. Awesome. Thank you. Thank you.
I have a question about the terminology regarding the divergent function, because divergence in physics means has a totally different meaning. Just mean the flow out of some area, and mathematics is the del operator, that vector field. So why is the choice for the naming?
We didn't choose it. Actually, it was chosen like in the literature like this. It's an error function. It could have been called error, but basically it's coming from like how it is diverging from how different it is. This is the actual meaning.
Okay, thank you.
Okay, if there are no other questions, let's take a break. Maybe 10 minutes, I think will be sufficient so that we try to finish early if we can. Assalamu alaikum. Shall we start?
Yes, we can start. Yes.
طيب, Bismillah ar-Rahman ar-Rahim. So, actually, this is a very nice tool by TensorFlow, which is one of the famous frameworks used for deep learning. It's called playground.tensorflow.org. It just shows us how we could actually train your network to detect boundaries, or either linear or nonlinear. So, for example, you have certain things to choose. You can choose how many hidden layers, like here, we don't have any hidden layer. If I just say plus, it will create for me a hidden layer, and then I can choose how many neurons in that hidden layer. I can create another hidden layer and so on. But since, so here we have like one neuron that would like it to detect the decision boundary between the blue and the orange. Now, since it is like a linear decision boundary, we know that it has to be only one neuron. You can choose here the activation function. So either ReLO or tan-H or sigmoid or linear to detect your basically decision boundary. So let's say we would like to use ReLO. You can choose the learning rate. So they have different parameters, so you can explore and choose. You can also use some regularization parameter to avoid basically overfitting. It has other problems like classification regression. So let's just show it for classification. Also, there are other parameters like what is the batch size. So here you see we said mini batch size. That means every 10 training samples, if we say 10, every 10 training samples, it will do one update for the parameters. So you can choose like what is the batch size that you want. Okay, and this is the ratio of the training data to testing data. So here it's chosen by default 50. You can increase it or decrease it. So we expect like one neuron should be sufficient actually to detect this decision boundary. And let's try and see if it can do that. So what it reports to here, the loss, okay, and the training loss and the testing loss. So we can see that very easily it actually created the decision boundary with 100% accuracy, okay? And this is the number of epochs it took like to do the training, so we can stop. Okay, so it's very easy actually to find this. If I try sigmoid, for example, and run it, it also reaches to 100% accuracy. All right, let's go to more complex decision boundaries. So for example, we have this, which has like non-linearly separable basically decision boundaries. So if we try to do that with one neuron, it's not gonna work, okay? It will try to solve it. As you can see, it is, the error is high, the loss is 0.55%, so it doesn't work. So we might go, okay, and let's go to add one hidden layer with two neurons and run this. And we can see that the training and testing loss are decreasing as we go, and it's trying to find the decision boundaries. Okay, now you can see that the error is still like high, and after like 1000 epoch, it couldn't like find the decision boundary. So we stop it. We say, okay, how about let's go with, let's go with like 4 neurons, 3, 4. Let's run that. Okay, we can see that it is now finding a decision boundary that actually classifies the points between the blue and the red. It is a bit slow, okay, like sigmoid. Like if we use ReLO, for example, it might come to a solution faster. Like, let me use ReLO. By the way, a ReLO activation function gives you 0 if the values are negative. It gives you 1 if the values are. It gives you the same value if it is positive. So this is very simple, actually. It's like the max between 0 and the input value. Okay, it didn't converge quickly. It is trying to find like boundaries. It succeeded here, but not like in that region. So this is how you can see whether like your network is struggling or not. In fact, the interesting thing, if you click here, you see that this perceptron is trying to detect this decision boundary. If you click here, you see that this perceptron is trying to detect this decision boundary, and this one trying to detect this one, and this one is trying. So we can see that like these two appear the same and these two appear the same. So that tells us that, okay, better to create like an additional hidden layer. Okay, so let's try with an additional hidden layer and see how it can do that. also struggling. So usually, although I think it was doing that with only, let me try to reduce this to 2 and 2. Okay, so the moment it doesn't like give you, you just have like to try to increase either the neurons in each layer or basically the number of layers until it's able to. You see now very easily, it actually detected the shape.
Dr. Ayman,
So, yes.
I'm running the same things, but I'm getting different result on the same setup.
Yes, because every time you see the parameters initialized randomly, so you might get different results.
Yeah, I got
Also
better
depending-
result, and what you got 0.03 for two test losses, I got 0.001. For
Yes.
this,
Every time you run it, like if I say a reset, it's gonna
Okay.
like give us different because like weights gets initialized differently. So
Okay.
you see, this is like what it got with Relo. If I run it with sigmoid, it's gonna give us like a different result. But eventually, it will classify, like it will be able to find the decision boundary. It will look a little bit different, but it will find the decision boundary. And you see that it found it, and the error, like for both the testing and the training data, is becoming very low. So kind of like this is like what it's doing. And if you click here, you can see each one, what is it really trying to classify? Like each one is doing some decision boundary here, like horizontal, vertical, another horizontal. And by looking at these, you can see that maybe some of them are redundant. Like you can see this one and this one look very similar. Okay, so maybe one of them could be eliminated and you could get the same result. So this is just illustration too. Okay, now I'm gonna show you, so let me stop the sharing and share a notebook with you where we are going to, okay, how can I go to? How can I hide the bar from Zoom so that I can have access to the top?
Sorry,
Now, how can I hide the bar from Zoom?
sorry, I didn't get it. The Zoom bar?
Is there a way to hide the upper bar from Zoom so that I can have access to the web pages?
You can just reposition it somewhere. You cannot hide it because that basically is like.
Okay, let me try to
sharing
resize.
control.
Yeah, I'm trying to resize my
So you
screen.
can try to move it around.
Yeah,
If you put it on the side, then you can have access to the top of the.
Actually, my suggestion is stop the sharing and then adjust everything and have a separate tab for instead of multiple tabs. Just have one tab and
All
share
right,
that one single tab.
let me try to do that.
Yes, please.
Okay, let me see which notebook I would like. So as I told you, you can go, like if you say colab.google, it's going to give you like this kind of screen, and then you can upload or open a new a notebook. So, okay, let me start with, yeah, so here what we have this notebook. So can you see the notebook?
Yes, we can see it.
Okay, actually this notebook, we gave it as a programming assignment for the neural network part this summer to the students. And we told them that we would like actually to detect objects inside this shape. Okay, so we have this shape. and we would like to detect like objects inside this shape. So design a neural network to detect objects inside that shape. So anything inside the shape, your network should produce a 1. Otherwise, it should produce a 0. So we ask him to design the network first, and then generate the training samples. So randomly generate samples where x1 goes from 0 to 8, and basically x2 goes from 0 to 10. So you'll get all the points inside and outside the shape, and then use this sample to test like your network that you have designed, whether you really did it well. If you did it well, you will get 100% accuracy. Otherwise, you'll get an error. So to design this, based on the knowledge that we have covered so far, students are expected to come and say, well, I'm going to divide this shape into 2 shapes. I have a rectangle and I have a triangle here. And then I will detect shapes inside the rectangle or inside the triangle. Now, to detect shapes inside the rectangle, I have 4 decision boundaries. So they have to find the equation of each line, rearrange it to be in the form greater than or equal to 0, find the weights and biases. And then they have to use an AND gate to say that it is basically to the right of this line, to the left of this line, above this line, and below this line. So 4 neurons with 1 neuron for the AND gate. Now for the second one, how many neurons do we need for the triangle? Do we need 3? We have 3 decision boundaries. We don't need 3. Why? Because I already have this decision boundary that I can reuse that was used for the triangle. However, it was used for detecting things below the line. Now I want to use it to be above the line. So all I need to do is just like invert basically the output of that neuron. So make it like an inverted. This is like the same. I already have that decision boundary neuron. I can share it also. So I only need 1 extra neuron for detecting this decision boundary, and then with an AND gate. So the first layer, I just need 5 neurons, 1 for each decision boundary. The second layer, I need like 2 AND gates, 1 for detecting things inside the triangle and 1 for the rectangle. And then a third layer, the output layer, which is an OR. So the students design it and come up with the weights. And then once they come up with the weights, they have to test their network. So we asked them actually to generate the points that they have to use for training and for testing. So here, basically in Python, that can be very easily done using a random uniform function. You give it the low value, the high value, and how many points you want. It returns to you that for second, like for the x1, x-axis, y-axis for x2. And then we produce what should be the output. Say y should be 1 if x1 greater than or equal to, and x1 less than or equal 6, and x2 greater than or equal 2, and x2 less than or equal 6. So this is like for the triangle. Or it has to be for the triangle, which is x1 less than or equal 6, x2 greater than or equal 6. And this is the equation of the line for the triangle. x2 should be less than or equal x1 plus 2. So this will produce the desired output. And then we concatenate the coordinates, we return x, we return xy. So this function, you give it how many points you want, it will like randomly generate the number of points. If you tell it like 10,000 points, and generate for you either the output should be 1 or 0, depending whether it is inside the shape or outside the shape. Then we ask the students like to generate training samples of 20,000, okay, and testing sample of 1,000. So these are generated randomly by calling the function here. Then now we have designed the threshold function because this is not like built in. Now they have to build their model. So after they design their neural network, this is how you build actually the neural network model. You just say it's a sequential model, and then you add them layer by layer. So we say model 1.add. So you say I want a dense layer, which means fully connected layer. And this is like how many neurons you want in the first hidden layer. So we said we need 5 should be sufficient. So we say 5. And the input shape, we have only 2 variables. So it is like 2. And the activation function that we'll be using is threshold, which we defined up. Okay. Now, then we add the second layer. We say it is dense 2. So we need 2 neurons in the second layer, which is like implementing the AND gate. Again, using the activation threshold. I don't need to say the input because the output of that layer will be input to this layer. And then a third layer, which is the output layer, we just say 1, okay, with an activation threshold. So this is how you create your neural network, like layer by adding them this way. Then you say, okay, I would like to compile that model. So you tell it like the optimizer. We said there are several one of them. The most famous one is Adam. So use like Adam. Now the loss function here, we use like a function called cross entropy. So binary cross entropy. So this is like better actually than the Euclidean distance. It's like very well known for using classification of one output. And then what is the metrics? We talked about like accuracy, F1 score, precision, and so on. So you choose what is your metric that you want to use to report your data. So here the students designed this network based on their like solution, and then they have to assign the weights. Now they have derived the weights for each layer. Okay, so this is like the first input to the first neuron, the first input to the second neuron, the first input to the third neuron, first input, and so on. So these are the values of the weights of the first input, how they are connected to the neurons in the first layer. These are the values of the basically second input, the weights of the connections between the second input and all the 5 neurons. And these are the biases, okay? Then the second layer, again, they do the weights, and then the biases and the weights and the biases. So they are given this, so they just have to fill the weights and biases. And now we defined actually, like they can actually print the weights and biases. We gave them a code so that they can debug their information. So this code, we will go over all the layers and print the weights and biases in each layer. Now we created this function. This function, which is called, you give it the model, you give it the data points, it's gonna predict the points that are supposed to be inside the shape as green and those that are supposed to be outside the shape as red. So it's gonna classify them and plot them. So that was given to them. And also the how to evaluate the accuracy of your model. So you're gonna give it the data, it will do the prediction and produce the output, and then we can compute actually the accuracy by computing the mean difference between the whether test y is equal to the whatever we have produced by our model. So this is the actual labels, and this is the what our neural network. So you compute the average of how many were basically equal, and that will give us the accuracy. So now we tell the students, well, you see, when I run the this basically code to compute the accuracy for the training data and for the testing data, I get 100% accuracy for both models. That means that my model was correct, was designed correctly. Otherwise, I wouldn't have gotten 100% accuracy. And then they plot actually what they, now we gave them also this code to debug, like in case it doesn't give them 100%. Now, if you plot, you see this is like for the training sample, you see that all the points that are inside have been colored green, which means predicted correctly, and all the points outside are the red ones, which, so you can see these are the points that were sampled actually randomly, and we can see that it's actually working very well. And the same thing, this is like for the test data, we can see that also for test data, because it has really 100% accuracy. So this is the first part where we ask them to design the network to take the shape and verify their answer by actually measuring the accuracy and plotting the data. The second part, we tell them, okay, now take a network and build it such that the first, basically, we call it model 2. Again, the first layer will have 5 neurons, but now use ReLO as an activation function. Okay, second layer will have 2 neurons, use ReLO also as an activation function. And the third layer has 1 neuron and use sigmoid. Okay, so now this network that we build here is going to be used for training. So they will use it actually to train, and we're going to use the same thing, Adam, binary cross entropy, and accuracy. Now to train the network, once they build it, all they have to do is just say model2.fit and give it basically the training data, train X, and the labels. And you specify how many epochs you want. So we want to run it for 50 epochs. So if you look at this, it started actually with some accuracy. It ended with 97.67 accuracy for the training data. Okay, so it worked. It's giving like high accuracy. If we do it for the testing data, we can see that it gives us also around 97 points, very close to. So that means we did not overfit. The testing accuracy and the training accuracy are very similar. Then they can print actually the result. And we can see that, yes, there's some errors. For example, this point was supposed to be like classified as green. It has been classified as red. Okay, so there's like here mispredictions, the same thing. So there are some errors because our accuracy is not 100% for the training network. Now, if you want like higher accuracy, you might go and increase. We know that it can be solved by 5 boundaries as we did, but maybe if you give it like more neurons in the hidden layers, it might learn better, although 5 are sufficient, because it's just like gonna use optimization, and it might like converge to some point and may not reach really to the optimal solution. And that's it. So this was actually the first the programming assignment that we gave them on neural network, and students love it. Most of them did very well and did it correctly. So this is like one example of using the notebooks to illustrate and apply what they have learned in class. Now let me show you another example.
Dr. Ayman, this is your own examples, that's correct? Not from the website, I mean, from the Google.
No.
Okay.
Actually, what we did is we showed them a similar example for detecting objects inside the circle. But without designing it, we just showed them, okay, using training, how we can do that, so that they saw the process, how it can be trained, how the model is defined, how you compile, how do you like fit the model, how you test it. So they have seen a notebook which is similar before we gave them this assignment. So the new thing is that we gave them here a new shape, and we asked them, we would like to detect inside this shape, design it. That was not like given to them before.
شكرا يعطيك العافية.
So, Doctor, another question. You're
Yes.
exclusively using Google Colab, or are you using Jupyter Notebook or any other software?
Actually, yeah, we are using Google Colab, and the reason for that, we don't need to install anything. So you don't need to install anything. Everything is ready. So the students just like use the Google Colab. They don't have to install any tools, because otherwise we're going to use like our like laptops and so on. It can be done, but they have to go and install a lot of tools, and you know, students will start facing issues. And so just like to have a peace of mind, Google Colab, everything is installed. If something not installed, it will be installed in the notebook itself whenever we need it, but most tools are actually installed. Okay, I'm going to show you another notebook, which is like a very simple example, which is like the banknotes. So what we have some features, like 4 features about banknotes, and we classify them whether they are authentic or counterfeit. So we'd like to design a neural network to actually classify this. So this could be solved using machine learning, but in fact, this is the first example that we show the students how we can use neural networks to actually classify data in continuity with the machine learning part. Then, so let me go now to the notebook. So can you see the notebook or still in the Excel sheet?
In the Excel sheet.
Okay, so now this is like the notebook. So all I have to do, I have to upload the banknotes Excel sheet in the Google Drive. And I shared with you, you just say drive.google. Now you can upload whatever documents you want, and then you can access them as I'm showing here. Okay, so the first thing is that we would like to read the file, and it's very easy. Actually, just you have a function csv.reader, and you give it basically the whatever you labeled here, the file name that you want to open. And you just this, it will open it, and then you go over scanning the data row by row, and then you append it in, like in Python, there's like a dictionary structure. So you call basically evidence, which are the features for cells in row from the beginning until 3, and then the label is just like if row 4 equals 0, we make it 1. So here we reverse the label. If it is 0, we make it 1, otherwise it is 0. So it's just like processing the data after we have read it and storing it in data structure called data. All right. So next.
Sorry, out of curiosity, why did you flip the label?
I think it just like it was like the 0, non-authentic, and 1. So like if you want to detect the counterfeit, but it could have been.
Okay.
I mean, this is not our notebook. It's actually This is how it was done. Okay. So now we have the evidence, like is the data that, all the data that from raw evidence and labels. So we split, basically this will be the training and this will be the testing, the labels. And then we split it using a function. We have a function called train test split. All you have to do, just give it like your training data, the labels, and the percentage of like the test size. So this will give you 60% training data and 40% testing data, and it will store it like this: training, X testing, like these are labels, Y training, Y testing. And then we can actually now create the model. So to create the model, we create a sequential model. And then as we have seen in the previous example, we're gonna create the layers layer by layer. So say the first layer, I want to create 8 neurons, and the shape is 4 because I have 4 features. I'm gonna use the activation function as relo. Then I'm gonna add a second layer where just the output layer. So here we're just gonna use 1 layer for the hidden layer because our problem is very simple, and 1 output layer, and you can see we're using sigmoid. Okay, and then we compile the same thing. It's Adam optimizer, cross entropy, binary cross entropy, and accuracy. We just say model.fit, and we give it the training data and the labels, okay, and how many epochs, and then we evaluate. So let me run this. Actually, it is already run, so we can just show you the data. So you see, if training starts with 32% accuracy, and then it keeps increasing until it reaches like 98.42 accuracy. Now, whenever you train, you get 2 parameters. One is the loss, and one is the accuracy. So the accuracy is the accuracy measure, like the total classified correctly over the total. The loss is the value, the difference, what we call the error function or the divergence function. So it's like the average error that is computed, and the average error should decrease while the accuracy should increase. And for the testing accuracy, also it gets like 97%. So you can see it all, that if you're satisfied with this level, fine. Otherwise, you might go add extra layers of neurons and so. So these are 2 examples that we show the students of how we can use neural networks actually to classify data, whether we have features, as I showed you, or we generated the samples ourselves for detecting things inside the shape. All right, now let me go to the third part, which is about neural networks, convolutional neural networks, I mean. Okay, this part is actually an interesting type of neural networks because it is like used for, particularly for processing images, okay? And they do perfectly well for actually images because they process the data in a 2-dimensional manner rather than when we have like converted images into 1-dimensional vector for the fully connected layers. So first I'll just like briefly talk about image representation, and then what are convolutional neural networks? Where is the name coming from, convolution? So we'll talk about image convolution. And then another like important operation that is done, which is called pooling. And then what is the convolutional neural network structure and how it can be used actually for classifying objects. So the way images are represented actually, as you can see, like camera basically gets a picture and converts it depending on the illuminations into, it goes through lenses and then image sensor. And then at the end, it gives us like arrays of intensity values. So if the image is colored, we will have 3 like arrays, 1 for the red, 1 for the green, and 1 for the blue. And we call each one of them, like each dot in the image, a pixel. So the pixel gets represented by 3 values if the image is colored, and each value represents the intensity. So we usually use 8 bits to represent like a range between 0 up to 255 values. So this is the range of the intensities. If we're talking about grayscale image, from 0 up to 255, the range between black and white. Now for intensity, this is the intensity level for red, like 256 different intensity values, and 256 different intensity values for the green, and 256 for the blue. Now the combination of these will give us all the colors. So a pixel in that case will be represented by 3 values, each one for the red, one for the green, and one for the blue. Okay. So this is like an example of how it could be represented in grayscale and in colored images. So usually we might use values between 0 to 255, or we might use values between 0 to 1 by dividing by the largest value, which is 255. So we get the values to be intensities ranging between 0 and 1. So the image is represented as like row, number of rows and column, and the top left pixel is like named or numbered as 0, 0. So we go like this, and 0 represents black and 255 represents white if we're talking about grayscale images. So at the end, the image is represented by numbers. If it is colored, we'll have 3 channels, okay? So we say that we have an input that has 3 channels, one for the red, one for the green, and one for the blue. Okay, what are convolutional neural networks? It's basically what's called deep learning networks, because they can take an input image and then learn the weights and biases such that we take like important features in the image. At the end, it will classify whether this image is a person, is it a car, is it like an apple, orange, and so on. So we could have like a large number of objects that we would like to differentiate. For example, we can go to 1,000 different objects. So the nice thing about convolutional neural networks is that we don't tell them what features they need to learn. So it just like understood that the features they learn is that in the first layer, they will try to learn primitive features, maybe lines, edges, and so on. The next layer learns like more like features based on the previous layer, and so on. So this is just like the understanding, but we don't tell them how to learn and what to learn. So they will be learned actually automatically through the training process, and they will find out how basically to choose the weights and biases to give us the final conclusion that it's able to differentiate between those 1,000 classes that we would like to do. Convolutional neural networks were inspired actually by studying cats. So they look at how cats can differentiate between objects and so on. This is how it started. And then basically they built the idea from there, and it carried on. Okay, so it can actually capture the spatial and temporal dependencies in an image. So if we have a video, we can also like, it can capture the dependencies across time. In the, if it's just an image, it will capture because we process the data in 2-dimensional. So it can also capture the spatial dependence. All right, the first really important part about convolutional neural networks is what's called the convolutional layer. So the convolutional layer is just like applying a filter on an image that tries to detect certain features. So for example, if I have this image and I apply a filter F on it, I'm gonna get like a new image, okay? Depending on what that filter is trying to do. Maybe that filter wants to detect edges, maybe it wants to detect lines or corners and so on. So each filter is actually gonna try to do something, like to process that image to try to extract some features. We can design those features, but as I mentioned, the beauty of the training process is that those filters will be learned automatically, inherently, and we will not tell the neural network what filters to learn, what features to detect. It's gonna learn them by itself and find what are the filters that it should use and that best basically differentiate or solve the problem that we are attempting. All we have to do is just to tell it how many filters we need to use. So in each layer, for example, if I have a convolution layer, I'll tell it I want 10 filters. Each filter should be detecting something different, probably. Okay, so basically what we're gonna get, the neural network, we're gonna give it like input channels, like in this case, 3 input channels, and then we'll apply the convolutional operation on those channels, and it will try to detect some features on those. So image convolution is applying a filter that actually processes nearby pixels by multiplying the filter by the corresponding pixel values and then summing the result. Okay, and the filter is usually defined as an M by M matrix. So I can choose my filter to be 3 by 3. So that filter, to convolve the image, he is gonna apply the filter on a 3 by 3 matrix and compute like one output value, and then scan the whole image and apply the filter again on adjacent pixels. Like I can shift by 1 pixel or by 2 pixel, we call this a stride, and then compute again, apply the filter on the next values and so on and so forth until I get an output image. Okay, this way we are detecting. Now the filter should have values such that it's trying to detect something, some features that it's trying to detect. Now this example shows you just like how the convolution process is doing. So if this is my filter, I'm just like putting ones and zeros, but it doesn't have to be. And this is my image. So my image is 5 by 5 and my filter is 3 by 3. So this will produce for me an image of 3 by 3, assuming that I'm using a stride of 1, which means I shift by 1. So you just do the dot product of the corresponding values and sum them. So 1 times 1 plus 0 times 1 plus 1 times 1 and 0 times 0, 1 times 1, 0 times 1, 1 times 0, 0 times 0, 1 times 1, and you sum them, this gives you 4. So this will be the first value of applying that convolution. And then you shift. If your stride is 1, as shown in the image below in the display animation, it has a stride of 1. So it shifts like row-wise and column-wise by 1 when it computes the next value, without exceeding the image boundary. So this way we actually get the produced image. So we say this is the result of the convolution operation. Okay, so one neuron will, if it has one filter, every neuron will have a filter, and the filter actually represents the weights. You can see bias and weights. So these are the weights, and this is the bias. And the difference between the typical neural network that we have seen before and this is that the neuron will scan the whole image. So he's gonna like take this portion of the image, apply it on the neuron, and then compute the result. Then take the next portion of the image and apply it, compute the second value, and so on. So the one neuron is gonna scan the whole image and compute basically the convolution operation. So by how much we shift, column-wise, row-wise, that's called the stride, and it's the same number of shifts. So if I use a stride of 1, gonna be applied when I shift like column-wise or when I shift row-wise. Okay, I can use a stride 2 or whatever. So it depends like how much you want to overlap the filter application on that image. Okay, this is another example where we use a stride of 2. So as you can see, with a stride of 2, I'm gonna get a smaller image. So the filter size is 3 by 3. That will result in a smaller image if I use a stride of 2. So this is parameter. Like when you define your convolution layer, you can say what should be the stride that you would like to use in your convolution layer. Okay, so now we understand what's convolution and how it is computed. Now I'm going to show you an example. Like here's an example of a filter that was designed, okay, not learned. So where people say, okay, let's put -1 in all the values except the middle, we put 8. And if we apply this filter on this image, okay, we can see that we're going to get like a convolved image, which is like detection. I'm going to show you the notebook in a minute, which will show it in a clearer manner. But logically, why this detects edges, that where it is coming from? They say, okay, of all the values surrounding the middle pixel are the same, what will be the result if I apply this filter on the 3 by 3 values that have the same value? They will cancel each other because you have 8 minus 1s multiplied by the same value plus 8 times that value, so you will get 0. So that means you'll get what? Black. If the values are different, you're gonna get something like not black, maybe like higher, like very different, you will get like white. Less different, you will get like gray. So let me show you. We can apply actually the filter on this. Like we have a notebook that I shared with you where you can read the image and apply this filter and see the result. So let me try to share that. Yeah, so this is the notebook here. So you can see that what we do, again, I'm reading the bridge image from my Google Drive, okay, and displaying the image. So just like this is for displaying, and I'm defining my kernel. So I'm saying here that my kernel, they give me like a kernel which is 3 by 3 initialized by -1. I'm just like making the middle value to be it. So here I created the kernel and then I'm printing it. Then all you have to do to apply the filter, you just say CV2. So this is like the one of the famous libraries for computer vision. And then filter 2D, you give it the image and you give it basically the kernel. It will do and apply the filter. And then we actually save it in this image, which is called filter, and then we display it. If we just apply it, you see this is the original image that we have, and this is the resulting image after we applied the filter. So you can see that it's not like white and black. We see some blues and so on. So it actually give us, this is the result of the convolution operation. So it extracted some features which are the edges. You can see that it's actually highlighting the edges in the picture. Anything that's not edge have been turned to black or close to black. So this is an example of using the filter. Any questions so far? Or the convolution operation? Okay, let's go back to the slides. So we do the convolution operation to extract some features. So every filter that is going to be learned, and the filter is a neuron. So the parameters of the neuron are actually the weights, which are these ones that will be used to be applied in the convolution operation. Okay, and these values will be learned automatically while we do training. So each neuron we add is going to learn some filter, okay, that's going to be applied on the image. So if I use, for example, the first layer, 10 neurons, that means I'm asking basically the neural network to apply a convolution of the first filter on the image, create another image. Another filter, the second neuron will apply a different filter on the same image, gonna create. So I'm gonna get 10 different images by the first layer. Now those images will be applied to the second layer and so on. So as you go, now the second layer will see these as inputs, the outputs of the first layer, and try to use the features from here to build on that knowledge and learn basically maybe higher level features and so on. Now, this is just like a formula to compute the size of the output. So if the image size originally is n by n and the filter size is m by m, and the stride s, then the resulting image will be n minus m over the stride and take the floor plus 1. So this will result in the reduction in the output size. If you don't want to reduce the output size of the size of your output image, you could pad it with 0 and then get like a similar size. So that can be done. Now here we just show the students examples, like of applying this formula. If we have an image size of 5 by 5, filter 3 by 3, stride by 1, we say, well, the result will be 3 by 3 image, and that's actually the result. If we use a stride of 2, the size is going to be 2 by 2. All right, now what is the structure of the convolution neural network? In fact, it has 3 main components or 3 main layers. The first layer is the convolution layer, and each convolutional filter is going to produce 1 output image. So showing here 3 output images, that means I have 3 neurons. Each neuron is going to produce 1 image. So if I want like 10 images to be produced, I must use 10 neurons. Each one will have a different filter. Then after we do this, we do like another layer, which is called pooling. And the pooling layer actually will go and process the images here, like to try to extract kind of like important features, be tolerant to noise. So it's basically kind of subsampling, reducing the size of the output produced. So if I have 3 images here, it's going to produce for me 3 images. And as we'll see in a few slides, the pooling layer does not have anything to learn. It's just going to do max operation or averaging operation. So it's not like neurons. So these are just computational nodes that will take these images and compute basically outputs. So there's no parameters to learn, nothing to train, just like computational nodes. This is the simplest convolution neural network, which has like convolution, And by the way, after we do convolution, it's not shown here, we do activation function. So we apply ReLO after the convolution, for example, ReLO or sigmoid or whatever. And then we do pooling. Once we do pooling, we take all the outputs and convert them into one-dimensional vector by concatenating them. So we make this one-dimensional vector, make this one-dimensional vector, this is one-dimensional vector, and concatenate them together into one-dimensional vector. That's called flattening. Okay, so take the output, convert it into like one-dimensional vector. Why? Because we want to feed it to a typical neural network, which is a fully connected neural network, now to do the rest of the job, classification or whatever, as we have done in the previous part. So this is the simplest convolution network. And in reality, I could have convolution layer, another convolution layer, and then pooling. Maybe then convolution, pooling. I could have as many like layers of these as I want. And eventually I'll do flattening and then do the feed forward network. Okay. So this is an example of a convolutional neural network. We have convolution layer, we have flattening layer, pooling layer, sorry, and then another convolution layer and another pooling layer. So it has 4 layers of 2 convolutions and 2 pooling, and then flattening and so on. Now, one thing very important to point out is that during convolution, every input channel has a different filter. And the convolution actually is done by multiplying the filter for that input channel by the portion that is got from the image. Take the second filter for the second channel, multiply it, and sum the result. You do for all of them, and then you sum the result, and that will give you one output value. So that output value is the result of multiplying each filter by the corresponding image, and then sum the result and getting the output. So as illustrated here, you see you multiply, you have 3 channels, so you have 3 filter channels, and each one is multiplied by the corresponding value to compute just one output value. We'll show a numerical example to show you this. So this means if I have 1 neuron here, and I have like 10 inputs, then for each basically input image, I'm gonna have different weights. So if my filter 3 by 3, and I have 10 inputs, then I need 10 3 by 3 filters, okay, for 1 neuron. So that neuron is gonna receive like 10 by 10, 10 times 3 times 3 is gonna receive 90, or it will have 90 weights to be learned for only that neuron just to produce one output. Okay, here's an example just to make it clear to students. Suppose we have 2 input channels, and we have 2 filter channels, okay, that's for a single neuron. How to compute the values? You're gonna multiply the first filter with the first 4 values, and the second filter with the corresponding 4 values, and sum all of them, and that will give you the output value from the convolution operation. And then you do stride of 2, so you multiply that filter by this window here, and then sum the result, multiply the second filter by the second window, and then the sum of both of them will give you a second value, and so on. So this is actually the convolution operation. And this is illustrated here more. For example, if I have 32 by 32 by 3 image, then my filter is 5 by 5. It also has to have the same number of channel depth as the number of inputs. If I have 3, I must have 3 filter channels. If I have 5, I must have 5 filter channels, and so on. So for each input channel, we will have a different filter. And this gets multiplied like that and producing at the end like an output, what we call it activation map or feature map. So all this done by a single neuron. Now, if I add another neuron, it's gonna do the same thing, but using different filters and gonna give me a different output. The third neuron, a different output, and so on. So in this case, I have 6 outputs. That means my network has 6 neurons. Each one of them is doing the convolution operation on basically that input image. So we told now the students how to compute the number of weights that need to be trained. We just simplified, we say, let's ignore biases. So say, well, the number of parameters that need to be trained if we have an image of size 32 by 32, and if we have basically a filter of size 5 by 5, now we have 3 input channels, we have 6 output channels. We said, okay, each neuron corresponds to 1 output. Since I have 6 output channels, I will have 6 neurons, okay? And now for each one of those neurons, how many weights do I have? For each filter, I have 5 by 5, 25 weights. And now for each input channel, I have a different filter channel. So that means for one neuron, it is going to be 3 times 5 times 5. Okay. Now, since I have 6 outputs, that means 6 neurons. Multiply this by 6, you will get the total number of weights. So the total number of basically weights to be trained in this case is going to be 5 by 5 by the number of inputs by the number of outputs will be 450. This is without the biases. If I want to add the biases, how many neurons I have 6. I'm just going to add 6. Okay, because I have 6 neurons. So then I have 6 biases. Each neuron has a bias. It's going to be 456. So this is like just for one convolution layer that has 6 outputs and it has 3 inputs, which is a red, green, blue image, and using a filter of size 5 by 5 in that case. Okay, the stride doesn't matter really for the parameters to be trained. It's just like the filter size is what matters. This is a computational example to show them like how to compute what I've just said, like for 3 input channels of size 6 by 6, 2 output channels using a filter of size 4 by 4. So how many weights need to be trained? Just like 3 times 4 by 4 times 2, and that will be the result. All right, now we said the convolutional layer is going to compute convolution operation and produce for us output image. Each neuron is going to produce one output image. Then what we do after we do ReLU activation function, we do what's called pooling layer. So the pooling layer, its objective is to decrease the computational power required to process the data that was produced by the convolutional layer through dimensionality reduction. So it will reduce the dimensions of the images, and also it's used for extracting the dominant features, which are rotational and positional kind of entirely. So here, what we're doing max pooling. So if we're using like a filter, which is of size 3 by 3, okay, what we are doing is we scan basically these like images and compute the maximum value and replace the 3 by 3 value by 3, okay? Here we're using a stride of 1, but in practice, usually the stride is the same as the filter size. So if I use 3 by 3, I use a stride of 3. But just for illustration, what we're doing, we're scanning the image and computing the maximum value. That's called max pooling, and replacing the 3 by 3 window by the maximum value. So this is why it's extracting dominant features. And at the same time, our result like reduce the dimensionality reduction. That's why I don't use a stride of 1. If I use, for example, a stride of 2 or 3, I'm going to get a much smaller image. So there are 2 types of like pooling operators, either the max pooling, which just replaces the corresponding values by the maximum. As you can see here, we have 20 or 30, and then 112, and then 37, or average pooling. So you replace the 4 values by their average for each corresponding basically window. Max pooling is more popular, produces better results. Now, I would like to emphasize, this is another example to show the difference between max pooling and mean pooling or average pooling. No parameters need to be learned during the pooling layer. These are not neurons. These are just like computational nodes. And the number of output channels in a pooling layer is the same as the number of input channels of the pooling layer. So if I have 8 input images, I'm going to produce 8 output images. Then once we do as many as we want, convolution, pooling, and so on, we do flattening. We take the result, for example, of one of the output images, and we convert it into a one-dimensional vector. If we have another image, we do the same, and then we concatenate them. Like we put the second vector after the first and so on. So that at the end, the output of the first, like all these layers that we added, just going to be a vector. So we're going to feed it to our fully connected neural network to give us basically the final result. So again, this is like the structure of the neural network. We said convolution, pooling. It doesn't have to be convolution followed by pooling right away. It could be convolution, and then pooling, convolution, pooling, or convolution, pooling. But then you do flattening, and then you do the feed-forward neural network. This is an example of like what people think could be learned. For example, if we have give like a neural network like faces versus cars versus elephants versus chairs, they This is not actually what's happening, but people think that this is what's being learned. In all of them, it's like, it doesn't matter like what is it, low level features. When you go about, you detect like higher level features. When you go about, you start seeing faces, you start seeing cars, elephants, and chairs. So this is like how people thought that actually what's going to be learned. But if you look at this example here, we have a car. You see that this is not actually the case. Here, for example, we give an image of a car, and we would like to differentiate between car, truck, airplane, ship, and horse. So we have here 5 classes to differentiate. So you see we do convolution, and you can see like this is the result of doing the convolution, followed by ReLU, then convolution, ReLU, and then we do pooling, convolution, ReLU, and then pooling, convolution, ReLU, and then pooling. And then we do flattening, and we do the fully connected layer. You can see that the highest probability came to the car. And then the next probability that this could be a truck, with some probability it could. So it gives you a probability. What is the probability that this is a horse? What is the probability that this is a ship? But the sum of the probabilities that it gives you, it should be 1. So then definitely this will be selected as a classified object because it has significantly higher probabilities than the others. So you see that it actually classifies things correctly. Of course, when you look at here, we as humans, we cannot see what is it really learning. How is it able to differentiate from the final layer here that this is a car, not a truck? So we really don't know the details of it. It just like gets trained and it finds out the features this way. So this is like a summary of the convolution neural network structure. We give it like a car. We have a convolution layer followed by ReLU, then maybe pooling, then another convolution followed by ReLU, then pooling, as many as we want. And then we flatten the structure, and then we have the fully connected layers. And at the end, we have our classes that we would like to classify using softmax activation function. This is actually one of the early convolution neural networks called LUNET-5, which was used for classifying the digits from 0 to 9. Given an input image of 32 by 32, like it takes it and then apply convolution layers with certain like filters. So you can see that it used here like 6 neurons in the first layer. Each neuron has a filter of 5 by 5. Okay. So this produced images of size 28 by 28. Then it used a pooling layer of 2 by 2 sampling with a stride of 2. And this reduced the images sizes into 14 by 14, the same number of basically images. Then another convolution layer where it used a larger number of neurons. So here, 1, 2, 3, 4, 5, 6, 7, 8, 16 neurons. Okay. And again, 5 by 5 convolution layer. And it produced basically images of size 10 by 10. Then again, 2 by 2 pooling that produced basically images of size by 5 by 5. Then flattening it and using fully connected layer. At the last output layer, we have 10 nodes, 10 neurons to classify between digits 0 to 9. Okay, these are the details of like how many neurons were used in the fully connected layer. We have 120 neurons in the first hidden layer, 84 neurons in the second layer, and finally 10 neurons in the last output layer. And it was able to detect actually objects. I will show you that we can build a much simpler network than this and get very high accuracy to detect actually digits. So let me go to that notebook where I'm going to show you how we can actually classify those digits using a convolutional neural network. Sure which one is this the one? No, not this one. Okay. Yeah, this one. Okay, so I shared with you also this notebook, which is called digits recognition. Okay, so what we do in this one, we are going to load the now this data is shared in basically MNIST library. So just say MNIST load data, it's going to load the data from there, which has the each image will be represented as one vector of pixel values, and then the labels. So we are basically loading the data into training and testing. It's already split and stored, so we just load it as is, okay? And then we normalize the training data by dividing it by the pixel values by 255, okay? Now, there's one thing interesting here that I would like to show you. If you print the labels, you will see that the labels are just like numbers, like 5, 6, 7. So it tells me what's a digit. We need to convert this into one hot representation because like my network has 10 outputs. So I need to produce the data in like 10 outputs, not like one label, which is 5. So by using this function to categorical and you give it the training data, we'll convert it you into a categorical form. So let me show you like how it does. So let me run it actually, because I can test like with you some samples. Of course, every time like you run a notebook and you're using the Google Drive, it's gonna ask you permission for connecting to the Google Drive. So you need to give it the permission through your Google account, and then it will access it. So every time you run the notebook, it does this, unless I'm not sure if you can select like to avoid asking you every time. So here, we're just like running the data. And look at, for example, this is like one label, which is 5. This is how it is stored in the data. I converted it into categorical. So it gives me now 10 values, and it puts 1 in the place of 5 and zeros otherwise. And we need to convert the data into this shape before we use it for training. Okay, so this is just like getting the data. And then we build our model. So we're gonna build our model. So we'll say, well, again, sequential, okay? So here, instead of doing add layers, we are adding the layers inside the sequential model. So we're saying, okay, we have a layer called convolutional 2D, okay? And we give it the parameters. So we say, okay, this is gonna produce like 32 outputs. So the first one is the number of outputs, okay? So that means give me 32 neurons, okay? And then the size of the filter, so 3 by 3. We said after we do convolution layer, we have to do activation like function. So you specify what is the activation function you want. So we say relo here, and then the input shape, it is 28 by 28 by 1. It has to be in this form, like kind of 3-dimensional form. So this is like we have one input channel. Like if it is colored image, that will be 3. So 28 by 28 by 3. So this is the number of channels in the input image. Then what we do, we say, okay, we want to add a max pooling layer. All we have to do is specify the pool size. So we say 2 by 2, the pooling size. Okay, so the output of the convolution will be feeding the pooling layer. And then we say, okay, so we just have one convolution layer, one pooling layer, and then we say just flatten my network, okay, to me. Then we say, well, now do dense. Now we'll do the fully connected layer. So I need the first hidden layer to be 128 neurons using relo activation. Okay. Now we didn't talk about this, like dropout. This is a technique that will ensure that the network will not overfit. So you can just like add it optionally. And then we say, okay, the second layer should be like another hidden layer with 10 neurons. This is actually our output layer. And the activation function here is softmax, which means what is going to be produced is probabilities. So for each output, what is the probability that it is digit 0? What's the probability that's digit 1, and so on. So when you use the softmax activation function, automatically it will produce for you outputs as probabilities. Then we compile the model using Adam optimizer. Notice here that we use cross entropy, but we say categorical, not binary, okay? Because we have multiple classes and we say categorical, that means we have basically one output for each class. And the metric is accuracy. Okay, so we can run this, compile the model, just compiled it. And then after that, we can train it. Now the training takes time because convolution layer is actually more complex to train than fully connected layer. So you can see that I just told it 8 epochs, okay? Each epoch takes like around like 51 seconds to train. But you can see it starts quite high, like accuracy of 92% from the beginning, and then starts improving until it reaches like 99%. Just one convolution layer, one pooling layer, and it gives really very high accuracy. Now, also for the testing data, it gave like 98.8. So what you can do whenever you deal with tasks that take time for training, after training, you can model, save the model. So you can just like run this and it will save the model, just give it a name and it will save it for you. I already saved the model. So now if I want, instead of like, because I didn't train now, so what I can do, just I ask it to load the model for me. So I load the model. Now I can use it to test like my model. Okay. So what I'm doing here is I'm picking like I'm asking it to generate a random number for me. Okay. Between 0 and like the shape of the, basically the size of the testing data. And then I'm taking that number, normalizing it. I'm taking that basically sample, multiply it by 255, okay, to show the image, like because I want to show it as an image. So I scale it back to 255. So as you can see here, it happened to be the image for number 5. And then I predict, like I feed basically that input to my network and I tell it predict what is the actual result that is going to be produced. Okay, and I tell it .argmax, because it's going to generate for me 10 values, give me the maximum value, the maximum probability. And based on the maximum probability, give me the index of what you have classified. And then I print it. So you can see that the image was 5, it printed it as 5. It was classified correctly. Now I can run it randomly. So you know now, this is what? Is it 7 or 1? It looks like 1. So it predicted it as 1. If you run it again, it picks another one, again 1. So this is 6. You see, it's able to classify things correctly. Of course, not 100% accurately, because we have seen the accuracy is like 99 for training it and around close to 99. But if we run it like as many times as we want, we see most of the time actually it is classifying the images correctly. It's able to detect the digit correctly. So this is a very simple and nice example to show how convolutional neural networks could be actually used. We have other notebook for like fashions, like clothes, more sophisticated, but the same structure, the same idea, and the students see that actually it's able to detect the different shapes, like is this a shirt or a trouser or a sandal or a bag and so on. So we show them other notebooks also, but similar idea. So any questions so far?
Assalamu alaikum.
Alaikum salam.
Thank you very much for the interesting presentation. My question is the following. Now, is this true, the following statement? If we have more features, the prediction will be more accurate. If I want to reduce the number of features and I get the same accuracy, what will be the benefit?
Okay, now the advantage of the neural networks, if you give it more features than it needs, it's going to learn like the important features by itself. I don't have to tell it which features are important, which are not important. These are correlated. Automatically through the learning process, it will find what are really the important features that will make a difference.
Okay.
And you can find the features which are not important by looking at the weights. If you find like weights have very small value, that means these features are not really important. If you remove them, they will not make a difference. Those important features, you'll see that they have like more like significant weight values that they are making a difference. So this is how you could say, actually, you could, after training it, see which ones you could remove and which one you could actually keep, which are more important, which have been used. So this is the interesting thing is that we just like training using the gradient descent, and it's going to learn and find. So all you have to do, you define the structure. How many neurons, how many layers you want, what type of layers, convolution, what filter size to use. This is like your job to determine to the neuron. And then it will train and find for you basically the best that it could do within this structure.
Clear. But usually it takes a lot of time to eliminate the number of features.
It takes time, like the training those neural networks. We are talking like you could have neural networks that have millions of parameters to be trained. So it can take days. But the nice thing about Google Colab, it has like GPUs. It has also TensorFlow processing units. that you can use. You can just subscribe for, I think, $10 per month, and you can have access to them. Like right now, it is free. You can use it. You can even use some GPUs, but you will have limitations. If you want more access to more computational resources, you subscribe for $10 per month, and then you can use GPUs, TPUs, and so on. But it is, yeah, what actually made neural networks flourish is the computational power that we have and the huge amount of data that we have. Because if you have training data and you have computational power, this is all you need. And then it will give you, like, a neural network started back in the 80s or before, but I remember when I was doing master's student, there was a neural network course, and it seems like everybody tried neural network and everything after that. Like you see all kinds of papers, but then it died because we didn't have computational power sufficient to really give you good results. We didn't have also sufficient data. We didn't have the internet to really be able to train and so on. Now, once we have this, now you can see all the amazing results and the uses that it's used for.
Thank you.
I have a question about the future. Your thoughts about the future. When do you think we'll see medical application for image detection in radiology reports, X-ray or MRI?
They're already there.
Commercial. Already available commercially? Okay.
Yes. Look, I mean, hundreds of papers actually doing that and so on. And with the convolution neural networks, many interesting results already there.
But you still don't have it commercially, like in Saudi.
I'm not sure about commercial product, but a lot of research has been done in this area.
Okay, thank you.
Yeah, Dr. Ayman, they are in California. They are special teams, I think, leading by one professor there. They're doing image processing based on the same things what you talked today about it. They're doing, a lot of things. And based on medical image, they talk about cancer cells and how, for example, propagate fast and how they can make decision, how they can do all this stuff. I think there are some, as you mentioned, research there. It's correct.
Yeah, definitely. I mean, you see, neural networks have made a difference. In fact, like there was a competition called ImageNet in the 90s, and where there are like 1 million like training samples around like or over to differentiate between 1,000 objects. And the first like use of neural networks showed a big difference between like all the machine learning techniques. That made the difference from that time until today, where it flourished and people start using it in everything, basically. But you have to know, like, convolution neural network should be used like when you have two-dimensional data. Like you don't go when you have one-dimensional data and use neural network, convolution neural network. So it's basically for two-dimensional data to try to like benefit from the correlation, the spatial correlation that you have in the two dimensions. Okay, I'm left with a small part. Let me try to finish that. So, in fact, this just like shows you, maybe give you more insight. We said each neuron, what it does, it scans the image like this and does the convolution operation and produces like an output image. The second neuron is gonna do the same thing. The second neuron will scan the image and produce a second image. The third neuron will scan the image and so on. So each neuron is detecting like some features from that image, and this is like output by that image. Now the second layer, if I'm doing another convolution operation, now this neuron is gonna scan the 4 images here, and using a filter here, a filter here, a filter here, a filter here, to produce like one dot in the output image here. And then we'll scan the 4 images all together to produce one output image. The second neuron will do the same using different like filters to produce that image. Now, if you think about it, let's say the filter that was used by the first neuron was like 2 by 2. And the filter was used by the second neuron is 2 by 2. If you look at it, in fact, this is like as if this neuron was looking at the image in a 4 by 4 instead of 2 by 2, because he's looking here 2 by 2, and each dot here represents in the original image 2 by 2. So as if this neuron is scanning the original image, looking at a bigger window with 4 by 4, and so on for the subsequent layers. And this is why people say, okay, this is trying to detect small features, then next one detecting bigger features because he's looking at a bigger window, and so on. So this is like the process that is done in the convolution operation. And once you do this convolution, and then you do pooling, you do flattening, and you use a fully connected layer. So if you want to detect a flower, no matter where is the flower, up here or down, you should be able to detect it because you are scanning the whole image and trying to detect the features of the flower as you go over the network. Eventually, it will say, yes, there is a flower or no flower. So in summary, the convolutional neural network is a supervised basic learning technique that can be used to try to mimic actually how mammalians' vision system works. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and then the pooling layer, which acts as a downsampling layers that basically try to reduce the size and extract the dominant features. And the parameters of the network can be learned through the regular backpropagation algorithm, although it is like much more sophisticated because there are shared like elements as you scan the network. We didn't go over all these details, but it is like kind of similar idea of the backpropagation algorithm. And I come to the end of the presentation. I hope that you found it useful. If you have any questions, please go ahead and ask.
Doctor, I have a question. Can I ask now?
Yes, sure, go ahead.
Doctor, I want to know to use the neural network in sustainable supply chain area. So is it necessary to be expert in the programming era, or we can do it with just by Python?
All you need is
medium
some
level.
knowledge of Python, and you can learn Python in 1 week. Like if you go to YouTube, you will see like 1 week recording, like few hours, maybe 6 hours. You will learn Python. You will learn what you need from Python. And this is actually how I learned Python. I went to that YouTube video and I learned it this way. Of course, I have a computing background. I know like C before and so on. I had the logic programming, but still it should be easy. Because you see, what we use in these notebooks are not for the experts. You just say fit model, evaluate model. You just like, so you don't like, for the expert, like if you are really specializing in deep learning, you don't use these simplistic model. You actually yourself write the code to train and how to compute the error, and you go like more in depth because you want to be more sophisticated. But for this level of course, or anybody who is not expert, you can just use whatever we shared in the models, and it will work for you using the Keras, basically library.
And secondly, Doctor, is there any pre-modeled or hollow models are also available for the neural ones? Can we use them as?
Exactly. That's called transfer learning. If you like, you want to detect like, let's say, objects for your field, you can search for like, okay, what are the famous like convolutional neural networks for image detection? You will get like, for example, there is like Google net, there is many other nets, mobile net for the mobile phone, like it's more optimized. There are many, you can start with them and they're available. So you can just download them and with their parameters train, and then train them on like your training data just to fine tune the parameters. And usually they give good results.
Thank you, Doctor.
You're welcome.
طيب, if there are no more questions, so we say thank you so much for Dr. Ayman and for Dr. Ashraf for this really great, informative workshop on the machine and deep learning. Maybe you can arrange just from this, I mean, regarding the Python, we'll see if we can arrange also with the ICS department for a short, for something like this, regarding the Python. For faculty as well. Inshallah, we'll try if that's possible. Thank you so much for for joining us also today. And Assalamu alaikum.
Just I would like to add comment. If any one of you like, you have access to the Blackboard, which has the material. So if you have any questions, you try to run the notebooks, you face difficulty, you can ask me in the chat in Blackboard, and I'll be happy to help you.
Thank you, Doctor.
Okay. Mr. Sanallah, yes, you can
Assalamu
close.